This is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see about the classification of fiber, or you can say about the fibers. So our lecture topic will be fibers. First, figure 1 shows the periodic table. So this is the periodic table. Okay, the conventional metal are shown in yellow color, whereas the material of the advanced fiber are shown in blue color. So these are the conventional through which the metals, that means conventional metals are there, and these blue one, so like this one and these, right, are the advanced fiber material is there. It can be seen that the material of the advanced fiber are lighter than the conventional metal. So you see here, now this one beryllium is what is above this one. As we move from top to bottom, the weight of the that element is increasing, so these are above these things. So just see here, before this only are there. So from here we can say that what weight of these fibers are lighter than the this yellow color. Okay, these materials occupy higher position as compared to the metals in the periodic table. So except this one, if you will see, these are at the higher position. So this is in P block. Okay, so if you will move right to left like this one. Okay, so this will be after this mist. Once this 3d or d orbital will get over, then only the p orbital will start. Thus one can easily deduce that in general these materials have higher specific property, that is property per unit weight, than that of metals. So these have what a specific property is much better than the other metals. So this is the periodic table. So in this only we are right now, these are the conventional one and these are the advanced one. These are non-metals. So we are not just put here a periodic table so that we can classify here. So only our consideration is this yellow and blue one. Okay, now properties of fiber. A fiber is characterized geometrically not only by its very high length to diameter ratio, but by its near crystal size diameter. Right? Not only length to diameter, whatever the, like suppose this length is there and the diameter that we had seen already, it should be greater than 1000, then only we can say it's a long fiber. So that is not, if length and diameter is in that range, then we can say that is the fiber. Then internally how that is there, so that is what near crystal size diameter, so that the diameter size should be near to the crystal size. The common structural material aluminium, titanium and steel are listed for the purpose of comparison, right? So these are just for the comparison we are taking. However, a direct comparison between fiber and a structural metal is not valid, because fiber must have a surrounding matrix to perform in a structural member. So when we are using the fiber, then definitely some other things that matrix is required, but in case of directly metal, no other surrounding materials or matrix is required. So we cannot directly compare metal and fiber. Fiber we can compare when it's combined with the matrix, then only we can combine. Otherwise it's like that you are just one is complete metal and another one is half, so we cannot compare. Okay, now whereas structural metal are ready to use, so whatever the structural metal are like iron, copper, these are ready to use directly, we can use, but fibers we cannot use directly. Fiber we can use along with the matrix only. Note that the density of each material is listed because the strength to density and stiffness to density ratios are commonly used as indicator of the effectiveness of a fiber. Means strength to density, how much is there, means this material having density, then how much strength is there, then is density and stiffness ratio, right? So these are the properties which shows the effectiveness of the fiber. Means if a strength is greater compared with respect to density, then we can say okay, this fiber is useful. Similarly, that fiber should be stiffer also when we will compare with the density, especially in weight sensitive applications. So where weight is required, that means weight sensitive application is there these two, like a strength to density and a stiffness to density, or you can say a strength to weight ratio and a stiffness to weight ratios is very important in aircraft and space vehicle. So where the weight sensitive applications are there, so these two are very important parameters in that case. Now see some types of fiber. So first one is what? Boron fiber. This fiber was first introduced by Paley in 1959. In commercial production of boron fiber, the method of chemical vapor deposition, that is, in short, it's called as CVD, is used. The CVD is a process in which one material deposited onto a substance to produce near theoretical density and a small grain size of the deposit material. So in CVD, what we are doing is the same. Material deposit onto a substrate to produce near. So on that substrate, one substrate will be there, on that only we are producing near to the theoretical density, what theoretically we are assuming near to that material, whatever is getting deposited on the substrate. In CVD, the material is deposited on a thin filament, right? So that is the substrate. So on thin filament, only material is deposited. The material grows on this substrate and produces a thicker filament. So now what happened? One thin filament is there as a substrate. Now materials start depositing, right? So what happened? Definitely this becomes thicker and thicker as much as the material will get deposited over that thin filament. The size of final filament is such that it could not be produced by drawing or other conventional method of producing fibers. So the final size up to that we have taken is that we cannot draw that one. Okay, so by drawing and other conventional method we cannot produce that one. It is the fine and dense structure of the deposition material which determines the strength and modulus of the fiber. So it is the fine and dense structure. Once we will get on deposited on the thin film that becomes thick, then we can say that will determines the strength and modulus of that fiber. In the fabrication of boron fiber by CVD, the boron trichloride is mixed with hydrogen and boron is deposited according to the reaction. So just see here what happened. So here actually 2BCl3 plus HCl will be there. HCl. Okay. That will give you what? 2 and 3H2. So just see, I am writing here once again. 2BCl3 in the gaseous form. Okay. And plus 3H2 will give what? 2B in solid form, that is in gaseous form, and plus 6HCl. So now just see that this is balanced or not. So this is 2Cl3. So total 6Cl we have. 6Cl is correct. 3H2, 6. Okay. So 2B. So this is the final reaction. So here this H2 is missing. Sorry, with this place. At this place, this gas is there. That is here actually this 2 is there, but that is H2 gas is there. So when it's combined with that's it, it's given here, mixed with the hydrogen. So 3 mole of hydrogen and 2 mole of BCl3 gas. When it's combined in the CVD process, then what we are getting? 2 moles of boron in the solid form and 6 moles of HCl that are in gaseous form. In the process, the passes take place for a couple of minutes. So in this way, that couple of minutes is required. During this process, the atom diffuses into tungsten core to produce the complete boridization. So here what happened? Tungsten is getting diffused to complete, or you can say tungsten act as a catalyst so that they increase the reaction, means complete boridization. In the beginning, the tungsten fiber of 12 micrometer is used. So in the beginning, the tungsten fiber of size of 12 micrometer is used. This step induces significant residual stresses in the fiber. So in this step only, the significant residual stresses in the fiber is achieved. The core is subjected to compression and the neighboring boron mantle is subjected to tension. So just see here, that is mantle, not in heated form, that one in CVD. So the core is subjected to compression and neighboring boron mantle is subjected to tension. So that means boron is subjected to tension and the core subject, that is what tungsten is experiencing the compression. Now, so that was the method of producing of boron fiber by CVD method. Now, key features of boron fiber. So what are the features of boron fiber that we will see? So first one is, these are ceramic monofilament fiber. So here this one is monofilament fiber, means only one filament fiber is producing. Fiber itself is a composite. Fiber also is a composite. Circular cross section, so that monofiber filament is produced is of circular cross section. Fiber diameter ranges between 33 to 400 micrometers. So their diameter ranges 33 to 400 micrometer, and typical diameter is 140 micrometers. That the typical diameter around is 140 micrometer. Boron is brittle, hence large diameter result in lower flexibility. So if because of the brittleness nature of the boron, what happen if larger diameter will be there, then the flexibility will reduce. So they will have the lower flexibility. Thermal coefficient mismatch between boron and tungsten result in thermal residual stresses. So earlier we had seen also what happened, thermal residual is generated. So that's why the reason is the coefficient mismatch between boron and tungsten. Their coefficient is not same, so that produces the residual stress during the fabrication, cool down to room temperature. So at the fabrication, they produce some residual. Boron fiber are usually coated with SiC, silicon carbide, or B4CSO. Okay, so this is CSO. Okay, that it protects the surface during contact with molten metal when it is used to reinforce light alloy. Further, it avoids the chemical reaction between the molten metal and fiber. So it again, what happened? It's not allowing chemical reaction between molten metal and fiber. Otherwise, what happened? Molten metal and fiber will combine. Then again, they will becomes in the molten state, and again the same procedure will be there. We won't get the fiber. So they are just separating, or they are not allowing to react with the molten metal. Strong in both tension and compression. Either tension force will be there or compression. In both the cases, this is strong. Exhibit linear axial stress strain relationship, means it's obey the Hooke's law. So their axial stress strain relationship is linear up to 650 degrees Celsius. So means up to 650 degrees Celsius, if you will heat that boron fiber, then it obeys the Hooke's law. Okay. Beyond that, their property will change. Then it won't be linear. Since this fiber requires a specialized procedure for fabrication, the cost of production is relatively high. So because here we are using CVD method, that a specialized method is there, so that's why the cost of production is high. Now come to carbon fiber, the second type of fiber. The first carbon fiber for commercial use was fabricated by Thomas Edison. So first carbon fiber invented, or you can say made by Thomas Edison. Sixth lightest element, and carbon-carbon covalent bond is the strongest in nature. So sixth, the carbon is what? Their mass is 6. So that is the sixth lightest element, and carbon-carbon covalent bond. So carbon having the property, they can form covalent bond. Carbon itself, of even in thousand numbers of carbon it can combine. So carbon having only that peculiar property. In that same group, you can see even carbon sulfurs are there. They can come. Sulfur also can combine up to 50, 60, up to like that only. Not even in thousands, but carbon can combine carbon thousands, that they can form a very long chain. So they have the peculiar property, and that be the covalent bond, and hence that is the strongest in nature. Those covalent bond is the strongest in nature. Means carbon when they are combining itself, that bond is very strong. Edison made carbon fiber from bamboo fiber. So he made that he used the bamboo fiber to make the carbon fiber. Bamboo fiber is made up of cellulose. So bamboo fiber is a natural, in nature we are getting the bamboo fiber that is made up of cellulose. Precursor fiber is carbonized rather than melting. So instead of this one, that precursor fiber what we use, instead of melting like previous in boron, case of boron, here it's getting carbonized. Means they are allowing to react with the carbon. Filament are made by controlled pyrolysis. So pyrolysis is the method where we are using the heating, right? So pyrolysis means where we are heating that thing. So filaments are made by controlled pyrolysis. Just here, controlled means that should be at that particular condition only, whatever the thing is required. The same temperature also, that should be at a specific temperature only, then only it can be produced. So see here it's written chemical deposition by heat. So when we using the heat, that process is called the pyrolysis of a precursor material in fiber form by heat treatment at temperature of 1000 to 3000 degrees Celsius. So see, at 1000 to 3000 degrees Celsius temperature is required, okay, for this method. the carbon content in carbon fiber is about 80 to 90%. So up to 80 to 90% carbon is there, and in graphite fiber the carbon content is in excess of 99%. So even if you see the graphite fiber, so this is carbon fiber, and in graphite fiber even it's greater than 99%. You can see almost graphite fiber having 100% carbon, but not exactly 100. It's just greater than 99. Some already we had seen that residue is formed, so some a small amount of less than 1% residue will be there, or you can say that impurities. Carbon fiber is produced at about 1300 degrees Celsius. So carbon fiber around 1300 degrees Celsius, while the graphite fiber is produced in excess of 1900 degrees Celsius. So graphite fiber produced at 1900, and carbon fiber produced at 1300 degrees Celsius. The carbon fiber becomes graphitized by heat treatment at temperature above 1800 degrees Celsius. So that's why at 1900 degrees Celsius we are preparing the graphite fiber. Why? Because at 1800 degrees Celsius carbon is getting graphitized. Means carbon converted into graphite. Right? And that's why we are using the 1900 degrees Celsius to produce the carbon fiber, means greater than 1800 degrees Celsius. Carbon fiber term is used for both carbon fiber and graphite fiber. So generally, if carbon fiber we are telling is that is both carbon fiber or graphite fiber. The difference is one is at 1300 degrees Celsius, and the other one, that is the graphite carbon, is produced at 1900 degrees Celsius. Different fiber have different morphology, origin, size, and shape. So depending upon the fiber, their morphology will be different. Size, shape, depending. The size of individual filament ranges from 3 to 147 micrometer. So there's the ranges that what filament ranges 3 to 147 micrometer. Either it will be 3 micrometer also, or up to 147 micrometer also, or in between in size. Maximum use of temperature of the fiber ranges from 250 degrees Celsius to 2000 degrees Celsius. So up to 250 to 2000 degrees Celsius we can use. So that's why up to 1900 degrees Celsius we are using for graphitize, means to getting carbon graphitized, so that we can get the graphite fiber. The use temperature of a composite is controlled by the use temperature of the matrix. So how we are controlling? By controlling the temperature of the matrix. Otherwise what happens if matrix temperature is too high and this one composite having that okay is lesser, then that will again it will get increased. Precursor material, they are two precursor material, that is polyacrylonitrile, that is called PAN, and second rayon pitch, that is the residue of petroleum refining. So rayon pitch we are getting from the residue, so that residue is there, so that from there you just convert into the carbon fiber. So these two are the precursors from which we are getting the carbon fiber or graphite fiber. Now, fiber properties vary with varying temperature. Since already we had seen at 1300 degrees Celsius it's the carbon fiber, and 1800 degrees Celsius it's getting graphitized, and at 1900 degrees Celsius we are getting what? Graphite fiber. So temperature changes means the property also will change. Fiber diameter ranges from 4 to 10 micrometer. So the diameter, that was the length, and this one is 4 to 10 micrometer their diameter. A tow consists of about 3000 to 30,000 filaments. Tow 3000 to 30,000 filaments are there. A small diameter resulting very flexible fiber and tied into a knot without breaking the fiber. Right. So this if flexible is there, then we can just like a small that very thin thread is there, we can tie a knot without breaking. But if very large is there, then without breaking we cannot tie a knot. Right. So it's a flexible means with that we can tie a knot. Okay. Modulus and strength is controlled by the process. So modulus and strength is controlled. The procedure involves the thermal decomposition of the organic precursor under well-controlled condition of temperature and stress. So these are this one. And that means under controlled condition, temperature, stress and all, only we can control the modulus and strength of that fiber. Cross section of fiber is non-circular. So cross section of that fiber is non-circular. Internally it is kidney bean shape. So it's of the what? Kidney bean shape type, not the circular one. Heterogeneous microstructure consisting of numerous lamellar ribbons. So lamellar ribbons means over. So that is in the ribbons form. Morphology is very dependent on the manufacturing process. So according to the manufacturing process, we will get the morphology. So that's why depending upon our requirement of the morphology, we have to use that type of manufacturing process. Or if whatever the manufacturing process we are using, according to that only we will get the morphology of the fiber. Pan-based carbon fiber typically have an onion skin appearance, means layer by layer, one over the other layer, with the basal planes in more or less circular arc. So they are almost just like, looks like what, onion one over the other, and that is almost just a circular arc. Whereas the morphology of pitch-based fiber is such that the basal planes lie along radial planes. That plane lies along the radial plane, but that along the vertical plane. Thus, carbon fibers are anisotropic. So this one is important. Carbon fibers are anisotropic in nature. Now, next one is glass fiber. So fibers of glass are produced by extruding molten glass. From molten glass only, we just extrude that one, we will get the fibers of glass at a temperature around 1200 degrees Celsius. So at 1200 degrees Celsius, first melt the glass. Once that is in the molten state, then it starts extruding. Means just start pulling or extension. That is called extruding. Right. So at 1000 degrees Celsius, then we will get the fiber through holes in a spinet with diameter of 1 to 2 mm. So now what happened? Just take the molten one, now put a spinet there, so that, and start extruding from there. So that diameter itself is 1 to 2 mm. So with the hole, if suppose this hole is there, right, and if anything we are pulling or pushing from this hole, then what happens? The shape also becomes the size of this one. So similar way, that with the 1 or 2 mm diameter, they are just pulling, so that now the diameter of that fiber also is of 1 to 2 mm. And then drawing the filament to produce fiber having diameters usually between 5 to 10. So first what we are doing, 1 to 2 mm, first we are drawing, and then later converting into the filament, so that to produce the fiber of diameter 5 to 15 micrometer. So first what you have to do, just molten glass is there, draw with what, 1 to 2 mm diameter, and after 1 to diameter, then draw in the form of filament. The fibers have low modulus but significantly higher stiffness. So they are low modulus, that's why it easily breaks, but stiffness is higher. Individual filaments are small in diameter. If you see the individual filaments, that is very small in diameter, isotropic and very flexible. So glass fiber is what? Isotropic and very flexible as the diameter is small. Since the diameter is small, so they are very flexible. The glass fiber come in variety of forms based on silica, which is combined with other element to create a specialty glass. So means how silica is combined with the other material, because from that only we can extrude the, after melting that glass, we are extruding and we are getting the fiber. So that depends on what? Based on silica, how silica is combined with the other element. So now just see based on that the different types of glasses there. So that is here. What are the different types of glass fiber? What are the key features? So these are the red color is the different type of glass, and this one is the feature. The type of glass fiber and their key features are as follows. So first, E-glass. E-glass having what? That is the first type, and their key features is what? Higher strength and high resistivity. So E-glass having higher strength and higher resistivity. Second one is S2 glass, having, that is their key feature is higher strength, modulus and stability under extreme temperature and corrosive environment. So they are not getting corrode and extreme temperature. So at the extreme temperature also it can sustain. So wherever we require the very high temperature, there we can use this to insulate that. R glass enhanced mechanical properties. So that type of glass is what? R glass, whose key property is what? Enhanced mechanical property. Means mechanical property like this one, mechanical property all we can enhance with this one. So not we can enhance, that is enhanced mechanical property. C glass resist corrosion in an acid environment. So in an acid environment, C glass also not getting corrode. D glass having good dielectric property. So these are the different types of glass and their key features. Now, next is alumina fiber. So this fiber we are using in aircraft mostly. Okay, so how? These are ceramics fabricated by spinning a slurry mix of alumina particle and additive to form a yarn, which is then subjected to controlled heating. So first, what in spinning a slurry mix of alumina particle and additives, okay, to form a yarn. So they first form yarn, and which is then subjected to controlled heating. After that, controlled heating is there, and then we will get the alumina fiber. Fiber retains strength at high temperature. So this fiber at higher temperature also can retain their strength. It also shows good electrical insulation at higher temperature. So alumina fiber at higher temperature also will have the good insulation property. It has good wear resistance and high hardness. So wear resistance, and that's why we can see that aluminum fiber at upper surface we are using the alumina. Why? Because even after the many this one wear resistance, that load of air and other things are, then also it's sustaining. So they have the good wear resistance and higher hardness also. The upper continuous use temperature is about 1700 degrees Celsius. The upper continuous, so around almost 1700 degrees Celsius we are using this one. Fiber of glass, carbon and alumina are supplied in the form of toes, also called rovings or strands, consisting of many individual continuous fiber filaments. So they are in the all already we had seen this toes was there. So they are supplying in the form of toes. DuPont, that Anderson, has developed a commercial grade alumina fiber known as alumina FP. Right? Already we had seen alumina and additives. Right? So now this is alumina FP. So here FP is added. What is that? Polycrystalline alumina, that fiber. So alumina FP fiber. Alumina FP fiber are compatible with both metal and resin matrix. So this we can use in both the cases, like metal or resin. So metal matrix as well as in the resin matrix. These fibers have a very high melting point, that is around 2100 degrees Celsius. At 2100 degrees Celsius it will melt. So before that, below that temperature we can use that one. They can withstand temperature up to 1000 degrees Celsius without any loss of strength and stiffness. Means up to the 1000 degrees Celsius if we will use, then they won't lose their strength. More than 1000 degree ones will be there, then they will start slowly losing their strength and stiffness, and finally at 2100 degrees Celsius it will get melted. Right? So up to 1000 degrees Celsius there is no change in their property, either strength or stiffness. Okay, so at this elevated temperature they exhibited high compressive strength when they are set in a matrix. So once they combine with the matrix, they are showing what? A higher compressive strength. The alumina whiskers are available and they exhibit excellent property. Alumina in the form of whiskers also are available and they are showing the excellent property. Alumina whiskers can have the tensile strength of 20700, means 20,700 megapascals. So that much tensile strength is there. And the tensile modulus of 427 gigapascal, or you can say this is 20.7 gigapascal, that much tensile strength. And this one, 4 tensile modulus is 427 gigapascal. What are the application of alumina fiber? So that application, the alumina has a unique combination of low thermal expansion, high thermal conductivity and high compressive strength. So because of these property only, alumina is widely used in aerospace structure. The combination of these property give good thermal shock resistance. So they are not fluctuating or they are not changing with the changing temperature. These property make alumina suitable for application in furnace use as crucible, tubes and thermocouples sheath. Okay, so there we can use alumina. The good wear resistance and high hardness property and hardness in making the components such as ball valves, piston pumps and deep drawing tools. So in these case we are using the alumina fiber. Now next one is aramid fiber. These fibers are from aromatic polyamide. So that's why means from aromatic and polyamide. So from that one. That is nylon family. So that is from the nylon family. Aramid is derived from AR, that is aromatic, and amide is amide. So aromatic and amide of polyamide is there. Examples of fiber from nylon family, that is what? Polyamide 6, that is nylon 6, and polyamide 6 6, that is nylon 6 6. So that is nylon 6 and nylon 6 6 we are using for this one. These are organic fibers. Melt a spoon from a liquid solution. So with this one, DuPont, again the scientists developed these fibers under the trade name Kevlar. So they given their name as Kevlar instead of using this one. So now that fiber becomes the Kevlar. From poly p phenylene tetrathalamide, that PPTL in short, p propylene tetrathalamide PPTL polymer. So this is made from p phenylene tetra, that means PPA. PPTA, Kevlar is made of from PPA polymer. Morphology of Kevlar is what? Radially arranged crystalline sheet resulting into anisotropic properties. So they have anisotropic properties. Filament diameter of the Kevlar is about 12 micrometer and partially flexible. So they are of the size of the diameter size of 12 micrometer and partially flexible. Aramid fiber having higher tensile strength, intermediate modulus, significantly lower strength in compression. So they have what? Lower strength in the case of compression. So there are 5 types of Kevlar. So 5 grades of Kevlar with varying engineering properties are available. So till date 5 Kevlars are there. Their name is Kevlar 29, first one Kevlar 49, then Kevlar 100, Kevlar 119, and Kevlar 129. So these are the 5 different types of Kevlar is available. Now next is silicon carbide fiber. Silicon carbide fibers are ceramic fiber. These fibers are produced in similar fashion as boron fibers are produced. So in the same way, just like boron fiber, silicon fiber also can be produced. The fiber are produced by 2 methods as follows. So first already we had seen CVD is what? By CVD method we used that boron fiber. So CVD on tungsten or carbon core. There in case of boron we use the tungsten. So here tungsten or carbon core can be used in CVD. And second method is Nickel-on, that is the trademark of that particular company by Nippon Carbon Japan. So this is from Nippon Carbon. They form that. That's why they're according to their name, and that's why here this TM is there, their trademark. So first, already we had seen, but see for the silicon carbide, CVD on tungsten or carbon core. First, this fiber is similar in size and microstructure to boron. So again, silicon also similar to boron. The fibers are produced on both tungsten and carbon cores. So this can be produced in case of both. These fibers are relatively stiff due to thicker diameter of the fiber. So this one is relatively stiffer due to thicker diameter of the fiber. So they have the thicker diameter. The diameter of the fiber is about 140 micrometer. The fibers have a strength in the range of 3.4 to 4 gigapascal. So their strength is up to 4 gigapascal, from 3.4 to 4 gigapascal. Failure strain is in the range of 0.1 to 0.8 to 1%. So their failure range is 0.1 to 8%. The Young modulus is about 430 gigapascal. The Young modulus of silicon carbide or SiC is 430 gigapascal. The fibers shows high structural stability and strength retention even at temperature above 1000 degrees Celsius. So even above 1000 degrees Celsius, just like carbon fiber or glass fiber, they can retain their property. Now, the CVD with CS3SiCl3 as the reactant and SiC is deposited on the core as follows. So how? CS3SiCl3, that gives, right, SiC plus 3HCl. So now we are getting this SiC fiber. Here all are these points. These are dotted here. Actually, this dot is not visible here. Right. The SiC fiber produced on a tungsten core with a diameter about 12 micrometers. So this one around 12 micrometer diameter. Next point is it shows a thin interfacial layer between the SiC mantle and the tungsten core. Third point is in case when carbon fiber is used. So here these all are the points. Actually this comes this side, so it's not visible. Right. So these all are the bullet points. Okay. So these all are the bullet points. Actually, I put it here, but it's not visible in this slide just because of the screen resolution. Okay. So first one is it shows a thin interfacial layer between SiC metal and the tungsten core. In case when carbon fiber is used, the fiber diameter of the carbon fiber is around 33 micrometers. So if carbon is used, then the diameter is of 33 micrometer. Both type of SiC fiber have smoother surface than a boron fiber. Both either with carbon or tungsten, whatever the SiC will be formed, they are having a smoother surface than the boron fiber. This is because there is a deposition of a small columnar grain as compared to conical nodulus in boron fiber. Right. So in nodulus, what happened in this one? Columnar grain is formed instead of conical nodulus. The SiC fiber produced with carbon core are used in light reinforced alloy. So where we are using with the carbon in light reinforced alloy. These fibers are produced with a surface coating. The composition of this coating varies from carbon rich from inner surface to silicon carbide at the outer surface. So at the inner surface we are keeping the carbon, the more number of carbon to the outer surface. That is silicon carbide at the outer surface. The fiber that are used to reinforce the titanium have a protective layer which varies from a carbon rich to silicon rich and again to a composition which is rich in carbon at the surface. So means in starting carbon rich, then silicon carbide rich, like that, and at the surface again the carbon rich will be there. The outer surface acts as a protective surface, and when it comes in contact with molten and highly reactive titanium, the fibers are made by specially material corporation under the trade name, okay, SC6. So we just given their name as SC6. The coating increases the fiber diameter by 6 micrometer. Already we had seen that 4 up to, and so now it's increased by 6 micrometer. The fiber has low failure stresses due to surface flaw. So at lower stress, it can't fail because of the surface flaw. The higher strength of the fiber is due to control defect at the core mental interface. So when we are forming the CVD, because of the core mental interface is controlled, so that's why defect is lesser, and because of that higher the strength is there. The strength of SiC fiber produced using CVD is seen to be anisotropic. So this, or you can say silicon carbide, is anisotropic in nature. The radial strength is significantly lower than the longitudinal tensile strength. Radial strength is what? Significantly lower than the, means radially it's a lesser strength compared to the longitudinal tensile strength. When the fibers are heated to about 800 degrees Celsius in air for a long period, they lose their strength due to oxidation of the carbon-rich outer layer. As we have seen, carbon-rich outer layer is there, so more than 100 degrees Celsius, once it will get heated, they get oxidized, and once getting oxidized, they start losing their strength. Now, second one is Nickel-on, that is trademarked by Nippon Carbon, Japan. So this type of fiber, the fibers are manufactured by process of controlled pyrolysis, chemical deposition by heat of a polymeric precursor. The fiber is homogeneously composed of ultra-fine beta SiC crystalline and carbon. The filament is similar to carbon fiber in size. So the filament is also similar to the carbon fiber. The diameter of the fiber is about 14 micrometer. We had seen that earlier it was 12 micrometer. So this is around 14 micrometer. The fiber is more flexible due to a smaller diameter. The diameter is small, so it's more flexible. The fibers are arranged in toes of 250 to 550 filament per toe. So in one toe, around 250 to 500 filaments are there. These fibers come in two grades. Okay, so first one is what? Ceramic grade, and second one is high volume resistivity grade. So in ceramic grade, what happens? Ceramic grade provides good high temperature performance and mechanical properties. So ceramic strength key feature is what? At higher temperature, the performance is good and mechanical property also. The second type is high volume resistivity grade. It is a low dielectric fiber, okay, and it has good electrical and mechanical property. Means high volume resistivity grade having good electrical as well as mechanical property, and that is used in dielectric structure. Now next, Uses of Nickel-ons fiber. These fibers are used to form fibrous products such as high temperature insulation filters, etc. So in high temperature insulators, we are using the Nickel-ons fiber, or in case of filters. These fibers have high resistance to chemical attack, hence these can be used in harsh environment. If harsh environment is there, then also there you can use, because they are almost right or very high resistance to the chemical attack. Okay, these are also used as a reinforcement in plastic, ceramic, and metal matrix composites. So nickel-on fiber can be used as a reinforcement also. Now, cross-sectional shape of the fiber. So these fibers having different cross-sectional shapes are there. So see, cross-sectional shape of fiber of various types we have studied above are different. Whatever that now, just the cross-sectional shape of the fiber, although is assumed to be circular, is not circular in general. The various cross-sectional shape of the fiber are shown in figure. So now this is the cross-section, and what are the types of fibers are there. So circular means what? Glass, carbon, organic fiber, alumina, silicon, carbide. These having the circular cross-section. Elliptical, alumina, and light. Triangular, silk, silicon carbide, viscose. Hexagonal, sapphire, that is Al2O3, viscose. Rounded, triangular, that is sapphire, Al2O3, single crystal fiber. So this is for viscose and this is for single crystal fiber. Our kidney beam, that carbon, that already we had seen, that is the form of kidney beam. Tri-level, that is for carbon rayon. So these are the diameter how these types of fibers having. Next, fiber properties. The following are the important points regarding the fiber properties: but density, axial modulus, axial coincidence ratio, axial tensile strength, and coefficient of thermal expansion are some of the important properties. So these are the important properties of the carbon that fiber. Advanced fiber exhibit a broad range of properties. So now this is for the conventional one. Even if advanced is there, we will have the broad range of properties. What this is properties of carbon fiber can vary significantly depending upon the fabrication process. So how it's getting fabricated already we had seen. Property will change according to that, or it depends on the fabrication method. For the advanced fiber studied above, one can attain either high modulus greater than 700 GPa or higher strength greater than 5 GPa, but not attainable simultaneously. So means either they will attain the higher modulus or higher strength at a time, one only, but both simultaneously, both cannot be achieved by the carbon fiber. SCS6, IM8, boron, and sapphire fibers offer the best combination of stiffness and strength, but have large diameter and thus limited flexibility. Means for these are like what? SCS6, IM8, boron, sapphire. These can achieve both simultaneously. Okay, but their stiffness becomes low. Why? Because their diameter size got increased. Okay, however, IM8 fibers are exception for flexibility, though in this case IM8 is slightly more flexible compared to the SCS6 and sapphires. The specific stiffness of some of these fibers is almost 13 times the structural metal. So these having the stiffness is 13 times the structural metal, like iron and all, whatever the structural metals are there, they have 13 times greater stiffness. Similarly, the specific strength of some of these fibers is almost 16 times of structural material. Their stiffness is 16 times greater. Weight saving when the composite of these fibers are used. So because of the flexiness and higher modulus and higher strength is there, so much lesser weight is required. Hence, weight saving is there when the composites of fiber are used. It's tremendous due to high specific stiffness and strength. So with lesser weight, also we can achieve the same stiffness and strength. Now, actual property of the composite is what? Fiber plus matrix are reduced. Specific property are reduced even further when the loading is in direction other than the length direction of the fiber. So specific property what happen will get reduced if along the direction of the length if it's not applied. Next is tolerable property, means we can tolerate, we can tailor depending upon our requirement. One can get the desired heat transfer or electrical conductivity with greater dynamics. So with this we can properly heat transfer and electrical conductivity. The increase fatigue resistance is attainable with the use of these fibers component. aging effect can be significantly lower. So whatever the effect is that can be lower than carbon fiber, contact fiber. Notes: the fibers are classified based on their value of modulus as follows. So these are the 5 types of fibers based on their modulus. So first one is what? Ultra high modulus type UHM. So UHM is for ultra high modulus. The modulus is greater than 450 GPa. Next is after that high modulus type HM, that is modulus between 350 to 450. If the GP that modulus is 350 to 450 gigapascal, then we can say that is the high modulus type. Intermediate modulus, their modulus is between 200 to 350 gigapascal. And the list is that last is low modulus and high tensile, that is HT. Okay, a modulus that is less than 100 GPa. Okay, so these are the different types of fibers. So this is the reference. Okay, for this video you can refer the NPTEL course. Okay, so if you have any doubt, you just comment on the video link, or itself you can contact me related to your doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.